So everything that we've talked about so far has been valence bond theory, VB theory, and that includes hybridization of the central atom to give sp, sp2, sp3, stuff like that. It is really great for describing the bonding in most molecules, and it does a good job if you're just like sitting around in a coffee shop, like I said earlier. You don't need fancy computers or anything like that for valence bond theory. But now we're going to look at, honestly, what is a better theory. It's called molecular orbital theory, and molecular orbital theory was built upon the quantum mechanical wave functions we talked about in chapter 3 in order to, and expanded then for molecules. So they take what was already complicated math and essentially make it even more complicated, which is crazy. And you might think, why would anybody want to do that? Well, valence bond theory is certainly not perfect. We're going to see that it doesn't do a very good job to talk about magnetism. So molecular orbital theory will be much better about talking about paramagnetism, and molecular orbital theory will actually talk about color better. We're not going to talk about that as much, but it does. And it does refer to the bonding a little bit more accurately than valence bond does. In molecular orbital theory, or MO theory, atomic orbitals are delocalized into molecular orbitals. So on the right-hand side is a molecular orbital diagram for dilithium. And if you're a Star Trek fan, hopefully you got excited just like I did just now. Dilithium was the energy source that the Starship Enterprise used to go to warp drive. Now, dilithium is a real compound, which is pretty cool. However, I don't think it can be applied towards warp drives. Darn it! But maybe one day, et cetera, et cetera. Anyway, don't worry about that. If you look on the molecular orbital diagram, on the left side, you have a lithium atom. And lithium, if you remember from chapter 3, is 1s2, 2s1. And that's what you're seeing like straight above it. Like here's the 1s2, here's the 2s1. Each electron, one spin up, one spin down, etc., etc. On the far right side, you see a second lithium atom, which is also 1s2, 2s1. So on the left and the right-hand side of molecular orbital diagrams, you often see the atomic orbitals. And then in the middle right there, all this stuff in dark blue, those are the dilithium molecular orbitals. And we'll talk about that here in a little bit. But it's important to realize that the left and the right-hand side, those are just atomic orbitals. And then it's the middle part, that's where these molecular orbitals are, the orbitals that form between the atoms. In a molecular orbital diagram, you'll have bonding and anti-bonding orbitals, and they're both important, and we'll talk about this. Bonding, you can probably imagine, makes the molecule stronger. Anti-bonding makes the molecule weaker. Unfortunately, MO is pretty complicated. I'm talking very, very complicated. And people talk about like quantum computing and stuff like that. Hey, that's where MO theory is great for it, because there's a lot of things that have to be calculated in order to get good results at. So one day, I hope my students will have what I call the TI 2000 calculator, and it'll be like the ultimate calculator, and you can put stuff in and it'll spit out all these molecular orbital diagrams. Oh, I can only imagine. However, not quite there yet. The TI 2000 that I want to see anyway hasn't come out yet. So in Chemistry 221, we're going to look at very simple kind of versions to see how this works. And we're going to look at only diatomics, which are two atom systems. And we're going to look at diatomics only from the first and second periods. So this isn't going to be a huge example set we're going to look at, but here's what's going to happen. We'll look at two atom systems. So we can look at, say, O2, and we can look at H2, but we won't look at things with 3 or more atoms. So for example, NH3, ammonia, and H2O, those have too many atoms. We won't look at them, unfortunately. We're going to look just at simple diatomics. And also, we're going to look at atoms only up to neon. So we'll look at things between hydrogen and neon, but we won't look, for example, at chlorine, Cl2, because that's third period, or bromine, or any of those kind of examples. So we're going to get a good sense as to what MO theory offers, and one day in another course you might then look at more sophisticated examples, and you can use this knowledge then to help make sense of what you're seeing, stuff like that.
Nitrogen is not magnetic. It is diamagnetic. All the electrons in the molecule are paired. Oxygen, however, interacts with a magnetic field because it is paramagnetic. This physical property indicates that molecular oxygen has unpaired electrons. Molecular orbital theory accounts for this fact, but valence bond theory does not.
If you look in the upper right-hand corner, this is the Lewis structure for O2, all right? And if you look at the Lewis structure, there's a double bond between the oxygens. Each oxygen has two sets of lone pairs, 4 electrons total. If you think about formal charges, the formal charges of oxygen are 0, all that kind of stuff, which is great. But if you look at it, all of the electrons are paired. Like each up has a down. Each of those is a pair of electrons, either a lone pair or a bonding pair. And you don't have any electrons by itself. And that's interesting because in the real world, as we saw in that video, oxygen sticks to magnets. It's paramagnetic. So it has odd electrons hanging out, kind of doing its own thing. And that's not what we see in the Lewis structure. Now, the Lewis structure, Vesper geometry, valence bond theory, they all predict that O2 would be diamagnetic. And in reality, O2 is very paramagnetic. So you can see right away then there's some problems with the valence bond theory. It's really good for most of the things, but it's not perfect. By the way, valence bond does a great job with dinitrogen, N2. When you do its Lewis structure, everything's diamagnetic, and nitrogen goes through the magnet no problem. But there are some issues, and oxygen is a classic example of where the valence bond theory kind of breaks down. So let's look at molecular orbital theory and see how it can predict the paramagnetism of O2. There's a couple of principles of molecular orbital theory that help as you go through this stuff. And some of these are pretty obvious, but I just want to go through them. So first of all, in science and chemistry, there's a big thing about symmetry, and this applies here. So what that means is that at the number of molecular orbitals you have equal the number of atomic orbitals that you put into it. So you're not going to create or destroy any orbitals. So for example, if you're going to make H2, each hydrogen has one 1s orbital. So two 1s atomic orbitals mean that this H2 molecule will have 2 molecular orbitals. On the other hand, for lithium, the dilithium thing we saw earlier, each lithium had a 1s and a 2s orbital, so each of them had 2 orbitals, 2 atoms and 2 orbitals each, that's 4 atomic orbitals. And the molecular orbitals that came out of it also have 4 molecular orbitals. So all the atomic orbitals you put in equal all the molecular orbitals that you put out. So here's a question you might see. If you combine 2 oxygen atoms, and remember each oxygen is 1s2, 2s2, 2p4, if you have 2 oxygen atoms that you combine to make a molecule, how many molecular orbitals will you expect to have? So what you need to do to answer this question is figure out how many atomic orbitals are on each oxygen. Well, the 1s is an atomic orbital, the 2s is an atomic orbital, so that's 2. But 2 p's, if you remember, 2 p's break up into x, y, and z. So each p orbital has 3 orbitals total. So that means there's 1 plus 1 plus 3. Each oxygen has 5 atomic orbitals. And since there's 2 oxygens, that's 10 atomic orbitals that we're putting in. So we would expect to have 10 molecular orbitals that come out. So the 1s, the 2s, and the 3 2p's on each oxygen combine to make 10 molecular orbitals. That's kind of the idea happening. Remember that p's have 3 orbitals, d's have 5 orbitals. If you had an f, it would have 7 orbitals, but we're not going to look at d's, f's, or anything like that. We're only going to look up to the 2p's in this section because of the limitations of what we're doing.
The bonding molecular orbital has greater electron density in the bond region. The anti-bonding molecular orbital has reduced electron density in the internuclear region.
When you combine atomic orbitals together, you have 2 possibilities. One of them makes the molecule stronger, and those are referred to as bonding orbitals. So in that kind of lower video right there, that showed when the 2 1s orbitals came together to make a strong bond, and that's a bonding orbital. On the other hand, you can have those same 2 1s orbitals combine, and in an unfriendly method, a method that makes the molecule weaker. weaker. And those are called anti-bonding orbitals. Now, both of these are basically head-to-head overlap of the atomic orbitals. So they're both given the same symbol sigma, but notice that the anti-bonding gets a sigma star. That star means that it's an anti-bonding orbital and it's not as strong. Now, the reason for bonding and anti-bonding goes back to wave theory, which is something you might see in physics. If two waves can combine, they can create a stronger wave. This is constructive wave interference, sometimes they call it. It makes for a stronger one. That's where the bonding comes from in molecular orbitals. On the other hand, you can have two waves combine in destructive ways, and that basically cancels out the wave. And this is where the anti-bonding comes from. So when two atomic orbitals come together, you're going to have a bonding one, which makes the molecule stronger, and you're going to have an anti-bonding one, which makes it weaker.